Okay, നമുക്ക് ഇന്ന് addition of angular momentum നോക്കാം. Addition of angular momentum നമ്മൾ പ്രോബ്ലംസ് നമ്മൾ എടുക്കുന്ന സമയത്ത് നമുക്കറിയാം സ്പിൻ we have to consider spin and angular momentum. അപ്പോൾ total angular momentum എന്ന് പറയുമ്പോൾ it may be the sum of the orbital angular momentum plus the spin angular momentum, or L1 and L2, or S1 plus S2, and so on. So the addition of angular momentum is encountered in all areas of modern physics. The total angular momentum of the electron in a hydrogen atom consists of two parts: an orbital part L, which is due to the orbiting motion of the electron around the proton, and a spin part S, which is due to the spinning motion of the electron about itself. Then addition of general formalism, consider two angular momentum J1 and J2. J1 may be orbital or J2 may be spin, which belong to different subspaces 1 and 2. J1 J2 may refer to distinct particles or to different properties of the same particle. The latter case may refer to the orbital and spin angular momenta of the same particle, assuming that the spin-orbit coupling is sufficiently weak. Then the space and spin degrees of freedom of the electron evolve independently of each other. And the J1 J2 satisfy the usual commutation relations of angular momenta, that is commutator J1 x J1 y equal to IH cross J1 z, and this follows the usual commutation relation. And since J1 J2 belongs to different spaces, their components commute. അപ്പോൾ നിങ്ങളിത് നോക്കുക, J1y J1z IH cross J1xi, J1z J1x IH cross J1yi, J2x J2y is equal to IH cross J2zi. ഇതിന് വേറൊരു മീനിങ് നമ്മൾ നേരത്തെ ഡിസ്കസ് ചെയ്തിട്ടുണ്ട്, that is simultaneous measurement of J1x and J1y. That means it gives a complex value. That means we cannot measure J1x and J1y simultaneously. If we measure the J1x and J1y simultaneously, we will get a complex value along J1z. Then if J1 J2 belongs to different spaces, their components commute. If they belongs to different spaces, we can measure, that is commutator J1j J2k equal to 0. If they represent two different spaces, that means we can simultaneously measure the angular momentum of two different spaces. Now denoting the joint eigenstates of J1 square and J1z by ket J1 M1, that this is the joint eigenstate. Ket J1 M1 is the joint eigenstate of J1 square and J1z, and ket J2 M2 is the joint eigenstate of J2 square and J2z. So J1 square ket J1 M1 equal to eigenvalue J1 into J1 plus 1 H cross square ket J1 M1. നമ്മൾ നേരത്തെ കണ്ടിട്ടുണ്ട്, ഇവിടെ നൊട്ടേഷൻസ് മാത്രമേ മാറുന്നുള്ളൂ. J സ്ക്വയറിന്റെ പകരം ഇവിടെ J1 സ്ക്വയർ ആണ്, J പകരം J1z ആണ്, ആൻഡ് J2 J2z ആയി. ഐഗൻ വാല്യൂസ് നമ്മൾ J1 പകരം J2 എന്ന് ഉപയോഗിക്കുന്നു കേട്ടോ. Dimensions of the spaces to which J1 and J2 belongs are given by 2J1 plus 1 and 2J2 plus 1 respectively. The operators J1 square and J1z are represented within the set of ket vector J1 M1 basis by square matrices of dimension 2J1 plus 1 into 2J1 plus 1, while J2 square and J2z representations by square matrices of dimension 2J2 plus 1 into 2J2 plus 1 within the set of eigenstate J2 M2 basis. Now consider two particles or two subspaces 1 and 2 together. The four operators J1 square, J2 square, They can thus jointly diagonalized by the same state, denoting their joint eigenstates by. Now we are considering the joint eigenstates of these two particles, 1 and 2, or two subspaces, 1 and 2. Joint eigenstate is ket J1, J2, M1, M2. Or we can write as a direct product of ket J1, M1, ket J2, M2. So we are simply assuming that direct product of these two ket states can be represented by this state vector. The coordinates J1, J2 are independent, and therefore we can write the joint eigenstate as J1 square ket J1, J2, M1, M2. അപ്പോൾ ഇവിടെ ശ്രദ്ധിക്കേണ്ടത് ഈ J1 is acting on the joint eigenstate. Then act ചെയ്യുമ്പോൾ only the J1 is responsible. J2 will be there, but it is not operating on the J1. So if J1 square is acting on the joint eigenstate get J1, J2, M1, M2, only the J1 values changes. So the eigenvalues J1 into J1 plus 1 H cross square, the same eigenstate. For J1Z, the M1 is responsible, so we will get M1 H cross, get the same eigenstate. For the J2, only J2 is responsible, so J2 square get J1, J2, M1, M2 gives J2 into J2 plus 1 H cross square, get the same eigenstate. Then J2Z in the case it is operating only on M2. So the eigenvalue is M2 H cross, the same state vector get J1, J2, M1, M2. And the get J1, J2, M1, M2 form a complete and orthonormal basis using this completeness relation. You can write catch J1, J2, M1, M2, bra J1, J2, M1, M2. You can write summation catch J1, M1, bra J1, M1, catch J2, M2, bra J2, M2. And the completeness relation gives that which is equal to 1. An orthonormal state bracket J1 prime, J2 prime, M1 prime, M2 prime, J1, J2, M1, M2 equal to Kronecker delta J1 prime, J1, Kronecker delta J2 prime, J2, Kronecker delta M1 prime, M1, Kronecker delta M2 prime, M2. Now we can introduce the ladder operator or step operators. J1 plus or minus J1x plus or minus I J1y, J2 plus or minus s equal to J2x plus or minus I J2y. And when they operate on the joint eigenstate vector get J1, J2, M1, M2, what will be the eigenvalues? We can see it is seen that J1 നേരത്തെ കണ്ടത് തന്നെയാണ് കേട്ടോ J1 plus or minus when it is operating on ket joint eigenstate J1, J2, M1, M2, the result will be it acts only on J1. So the result is H cross square root of J1 minus plus or plus M1 into J1 plus or minus M1 plus 1 get J1, J2, M1 plus or minus 1 M2. Only it is acting on the M1, J1 and M1. And similarly J2 is acting on the J2 and M2. Now the problem we are considering the problem of adding two angular momenta J1 and J2. So the total angular momenta J is equal to J1 plus J2. Then we have the commutation relation box Jx Jy equal IH plus Jz, Jy Jz IH plus Jx, Jz Jx equal to IH plus Jy. And now J1 square, J2 square, J square, J is a jointly commute, and therefore we can write J square equal to J1 square plus J2 square plus 2 J1Z J2Z plus J1 plus J2 plus J1 minus J2 minus, which leads to box J square J1 square equal to box J square J2 square equal to 0, and to J square Jz equal to box J1 square Jz equal to box J2 square Jz equal to 0. But in spite of the fact that J square Jz equal to 0, the operators J1 and J2z do not commute separately with J square. That is J square J1z is not equal to 0, J square and J2z not equal to 0. Since J1 square, J2 square, J square, Jz form a complete set of commuting operators, they can be diagonalized simultaneously by the same state, designating this joint eigenstate get J1, J2, Jm. Now we have J1 square get J1, J2, Jm is equal to it is acting on J1. So the result will be J1 into J1 plus 1 H cross square, the same eigenstate J1, J2, Jm. And similarly, J2 square, we will get J2 into J2 plus 1 H cross square. For J square, the eigenvalue is J into J plus 1 H cross square. For Jz, the eigenvalue is MH cross. The space where total angular momentum J operates is spanned by the basis, a set of ket Jm. This space is known as a product space. Now we can go for the Klebs-Gordon coefficients. Now let us go to the addition of J1 and J2. And this problem consists of, in essence, of obtaining the eigenvalues of J square and Jz and expressing the state ket Jm in terms of ket J1, J2, M1, M2. We should mention that ket Jm is the state in which J square and Jz have fixed values J into J plus 1 and M, but in general not a state in which the values of J1 Z and J2 Z are fixed. The set of ket J1, J2, M1, M2 and set of ket Jm basis can be connected by means of a transformation as follows. Inserting the identity operator as a sum over the complete basis ket J1, J2, M1, M2, we can write ket Jm, this is the state vector of Jm, which is a combined state of J1, J2, M1, M2. Then we can use we can represent ket Jm in terms of the J1, J2, M1, M2 basis, and we can connect them by using the completeness relation. The completeness relation which is represented by summation M1 equal to minus J1 to J1, summation M2 equal to minus J2 J2. Then get J1 J2 M1 M2 bra J1 J2 M1 M2. This is the completeness relation. The value is equal to 1. Therefore, we can write get Jm equal to get Jm. Then we can bring this get Jm. We can connect these two things together. So we will get bra J1 J2 M1 M2 get Jm. Then get J1 J2 M1 M2. Now we have represented the ket Jm in terms of the J1 J2 M1 M2 basis. Since the base is set of ket J1, J2, M1, M2 and set of ket Jm are both normalized, and this transformation must be unitary. The coefficients brag J1, J2, M1, M2, ket Jm, which depend only on the quantities J1, J2, J, M1, M2 and M, are the matrix elements of the unitary transformation which connects the set of ket Jm and set of ket J1, J2, M1, M2 bases. These coefficients are called the Klebs-Gordon coefficient, and these coefficients are called Klebs-Gordon coefficient. That means we can connect this state vector uh, to this state vector get J1, J2, M1, M2 using these coefficients. These coefficients are called Klebs-Gordon coefficients. These coefficients are taken to be real by convention. Hence, bra J1, J2, M1, M2 get Jm equal to bra Jm get J1, J2, M1, M2. And the orthonormalization of the Klebs-Gordon coefficients can be written as bra J prime summation M1 M2 bra J prime M prime get J1 J2 M1 M2 bra J1 J2 M1 M2 get Jm equal to delta J prime J delta M prime M. Since Klebs-Gordon coefficients are real, this relation can be written as get M1 M2 bra J1 J2 M1 M2 get J prime M prime bra J1 J2 M1 M2 get Jm equal to delta J prime J delta M prime M, and which leads to summation M1 M2 bra J1 J2 M1 M2 get Jm whole square equal to 1. Then the eigenvalues of J square and Jz. Let us study how to find the eigenvalues of J square and Jz in terms of J1 square, J2 square, J1 is and J2 is. First, since Jz equal to J1z plus J2z, we have M equal to M1 plus M2. Now find J in terms of J1 and J2. Since the maximum values of M1 M2 are M1 maximum equal to J1 and M2 maximum equal to J2, we have M maximum equal to M1 maximum plus M2 maximum equal to J1 plus J2. But since modulus of M less than or equal to J, then J maximum equal to J1 plus J2. And uh, and we can write summation J equal to J minimum to J maximum. 2J plus 1 values are there. So we can write 2J1 plus 1 into 2J2 plus 1, which leads to J minimum square equal to J1 minus J2 square and J minimum equal to modulus of J1 minus J2. So the values of J lies in between modulus of J1 minus J2 to J1 plus J2. So the allowed values of J proceeds in integer steps according to J equal to J1 minus J2, J1 minus J2 plus 1, J1 minus J2 plus 2, and then J1 plus J2 minus 1, finally J1 plus J2. So The values of j lies in between j1 minus j2 to j1 plus j2. If for every j, the allowed values of m are located within the range minus j to j, since j is a get jm equal to mh cross jm, bra j1 j2 m1 m2 j1 is equal to m1 h cross bra j1 j2 m1 m2, and bra j1 j2 m1 m2 j2 z is equal to m2 h cross bra j1 j2 m1 m2. We can write m minus m1 minus m2 bra j1 j2 m1 m2 get jm equal to 0, which shows that bra j1 j2 m1 m2 get jm is not 0 only when m1 minus m minus m1 minus m2 equal to 0. If m1 plus m2 not equal to m, bra j1 j2 m1 m2 get jm equal to 0. So for the Klebs-Gordon coefficients not be 0, we must simultaneously have m1 plus m2 equal to m, and j values varies between j1 minus j2 j1 plus j2. These are known as the selection rules for the Klebs-Gordon coefficient. Calculation of Klebs-Gordon coefficients. First, ഇത് ചോദിക്കുന്ന ഒരു ഇമ്പോർട്ടൻറ്റ് ക്വസ്റ്റ്യൻ ആണ്, എല്ലാ സെമസ്റ്ററിലും ചോദിക്കുന്നത്. എന്താണ് Klebs-Gordon coefficient എന്നുള്ളത്, then how do we calculate Klebs-Gordon coefficient or find the Klebs-Gordon coefficient of j1 j2 equal to 1 by 2 1 by 2 respectively, or 1 1 by 2 respectively. Now we can go to the session how to find the Klebs-Gordon coefficients. First, we should point out that Klebs-Gordon coefficients corresponding to the two limiting cases where m1 equal to j1, m2 equal to j2, j equal to j1 plus j2, m equal to j1 plus j2, and m1 equal to minus j1, m2 equal to minus j2, j equal to j1 plus j2, m equal to minus j1 plus j2 are equal to 1. Bra j1 j2 j1 j2 get j1 plus j2 j1 plus j2 equal to 1. Bra j1 j2 minus j1 minus j2 get j1 plus j2 minus j1 plus j2 equal to 1. And we can write get j1 plus j2 j1 plus j2 equal to bra j1 j2 j1 j2 get j1 plus j2 j1 plus j2 get j1 j2 j1 j2. Get j1 plus j2 minus j1 plus j2 equal to bra j1 j2 minus j1 minus j2 get j1 plus j2 minus j1 plus j2 get j1 j2 minus j1 minus j2. For this, we need to derive the recursion relation between the matrix elements of the unitary transformation between set of ket jm and set of ket j1 j2 m1 m2. Since when j1 j2 and j are fixed, the various Klebs-Gordon coefficients are related to one another by means of recursion relation. To find the recursion relation, we need to evaluate the matrix elements j1 j2 m1 m2 j plus or minus jm into different ways. First, allow j1 j plus or minus to act on the right, that is on ket jm. That means j1 j2 m1 m2 j plus or minus ket jm. That means this ket jm is acting on this jm. Then the result will be h cross square root of j minus plus or m j plus or minus m plus 1. J1, J2, M1, M2, get J M plus or minus 1. And we are allowing to operate the J plus or minus as J1 plus or minus plus J2 plus or minus, and finally we will get this relation. ഒരു പേപ്പറും പെൻ എടുത്തിട്ട് ഇത് എഴുതി നോക്കുക കേട്ടോ, ഡിറൈവ് ചെയ്ത് നോക്കാം, സിമ്പിളായിട്ട് ഇങ്ങനെ പോകും. And finally we will get the recursion relation for the club's codon coefficient as square root of j minus plus m, j plus or minus m plus 1, j1 j2 m1 m2 get j m plus or minus 1 equal to square root of j1 plus or minus m1, j1 minus or plus m1 plus 1, j1 j2 m1 minus plus m m2 jm plus square root of j2 plus or minus m2, j2 minus plus m2 plus 1, j1 j2 m1 m2 minus or plus 1 jm. And this relation we can use for finding the Klebs-Codon coefficients, to find all the Klebs-Codon coefficients. അപ്പോൾ അതെങ്ങനെയാണെന്നുള്ളത് നമുക്ക് ഒരു എക്സാമ്പിൾ ചെയ്ത് നോക്കാം, നമുക്ക് എങ്ങനെ കണ്ടുപിടിക്കാമെന്നുള്ളത്. എക്സാമ്പിൾ ഞാൻ അടുത്ത വീഡിയോയിൽ ഷെയർ ചെയ്തിട്ടുണ്ട് കേട്ടോ. ഇതോടുകൂടി നമ്മൾ ക്വാണ്ടം മെക്കാനിക്സ് ഞാൻ എടുക്കുന്ന പോർഷൻ തീർന്നു. ഞാൻ നിങ്ങൾക്ക് ഗൂഗിൾ ക്ലാസ് റൂമിൽ അസൈൻമെന്റ് ഇന്റേണൽ ടെസ്റ്റ് ഒക്കെ തന്നിട്ടുണ്ട്, അതെല്ലാം കംപ്ലീറ്റ് ചെയ്യുക. ഇതോടുകൂടി നമ്മൾ ക്വാണ്ടം മെക്കാനിക്സ് തീർന്നു കേട്ടോ. ഓക്കെ, താങ്ക് യു ഫോർ യുവർ കോപ്പറേഷൻ.